Welcome to EE World. I'm Editor Martin Rowe. Wi-Fi 7 is going to bring new features to the ubiquitous Wi-Fi that we all have in our homes. But what will it do? One of those things is the ability to, in a mesh network, connect nodes using different frequency bands, a front haul and a back haul, you might call it. And how is it going to connect all of those? And how is it going to manage? And what happens when you walk around a house? And if you're using different frequency bands, how is it going to manage that and schedule that and aggregate those to get maximum data rates? To learn more about Wi-Fi 7, EE World spoke with Fanny Mlinarsky. Fanny has been around Wi-Fi testing for many years, having started Azimuth Systems and later Octoscope. Azimuth Systems was later acquired by Anritsu, and in 2021, Octoscope was acquired by Spirent Communications. This interview took place on December 20th, 2022. Soon after that, Fanny left Spirent to become managing partner at Quadrascope Venture Fund. Fanny, thank you for being with us at EE World. You have been around Wi-Fi for a long time, and your company, before it was acquired by Spirent, had developed quite a few products for testing Wi-Fi. And I know you've always been, I've always considered you my go-to person when it came to Wi-Fi and testing and so on. So Fanny, I know you've been keeping up with Wi-Fi 7. What's the status of Wi-Fi 7 in terms of the standards, in terms of what the semiconductor companies are doing, and what the test companies and what your company has to do, because chips are no good if you can't test them.
Right. Well, good question. And you said I have been around Wi-Fi for a long time, and my goodness, how far we have come. I have started in Wi-Fi in 2001, if you can believe it. And anyway, so we're looking, Martin, at Wi-Fi 7, which is now going to be transmitting data at above 10 gigabit per second over the air. It's going to beat 10 gig Ethernet. So now where it is, we have some samples. So we have radios that we can connect and play Wi-Fi 7 in our testbed. There are plug fests underway. And I can tell you a little bit about what Wi-Fi 7 brings to the world.
Tell us.
Where we are is we step, first of all, in channel width from 160 megahertz wide channels for Wi-Fi 6, 6E over to 320 megahertz wide channels for Wi-Fi 7. So we have doubled the channel width, and we have stepped up to 4K QAM. That means 4096 QAM constellation. It looks really frightening. It's amazing data rates, and it's amazing channel width to operate for any radio. But on top of it, we have 21st century intelligence built in to make it more efficient and to use every bit of resources available to us. So what does that mean? So on top of just the sheer radio capacity, we have a way to do multi-link operation. And what that means is if our radio has, for example, 2.4 gigahertz band and 5 gigahertz band and 6 gigahertz band, well, that's 3 radios. and we can multi-link them and have a link that has the capacity of all three added together. Now, what else can we do? It's really a system level optimization, and it's really cool because when you have a mesh network, some of your listeners will be familiar to your readers that we have a backhaul of that mesh and we have a front haul. The front haul is serving client devices, and the backhaul forwards the data among the mesh nodes. And typically there are 2 or 3 mesh nodes. And so the data is forwarded through them to the root node, which is normally connected to the internet and gives us the uplink. So you have these nodes, each has 3 radios and has 3 bands. And so what they can do is, depending on the traffic flow, if there's more traffic, say, going to the clients versus the backhaul, they can repoint these radios and they can time multiplex the radios being on the front haul versus the backhaul. Okay, and that's on top of this multi-link. And so this is crazy optimized using the latest processing power that we have for these APs.
Are you saying that not only can Wi-Fi 7 use multiple channels within a frequency band, such as 2.4 gigahertz, 5 gigahertz, and 6 gigahertz, but it can use channels across those bands in aggregate to increase data rate? How does the Wi-Fi device decide which channels to use and when?
It can hop around and use combination or aggregation for this optimal throughput. And it can do that with a scheduler, okay? So a scheduler can decide, okay, now I'm going to serve clients on 3 channels and they will not be aggregated because I have clients on all 3 channels. And then the next packet, it can say, now I need all my processing power in the backhaul, and I'm going to aggregate all these 3 bands and go shovel a whole lot of traffic across the backhaul for the optimum efficiency. So it's not just the sheer radio capacity, it's intelligence behind it, it's the scheduling.
Fanny, are you saying that not only can Wi-Fi 7 use multiple channels within a frequency band, how will Wi-Fi 7's scheduler manage the data on both the front haul and back haul, given that both can use the same channels?
We are the test people, and we're hooking it up and verifying it. Now, the thing to remember is to achieve the maximum performance, you need a system level test, right? Because in the past, your backhaul, you say, okay, I'm just going to use 6 gigahertz band for backhaul. Okay, so that's it. You just put some radios on it and they're fixed on that backhaul. You can't use them for anything else. What if most of the traffic is on the front haul? Then you just have the 6 gigahertz dedicated for the backhaul and you're wasting that bandwidth. So then Wi-Fi 7 improves on it and says, well, we're not going to waste that bandwidth, but now you've added scheduling complexity. And it's in response to what's happening on the network. And so that's very complex software. And how often does complex software work in its first revision? We're going to find some issues, but it's a complex test and it has to be a system test because of this scheduling complexity. So you can no longer just say, okay, we have this radio, we have doubled the bandwidth, we've quadrupled the data rate with 4K QAM, now we have the radio, we can go test it. And so simplistically, yes, you can, but really you're not testing all the improvements in the performance. You're not testing all the 21st century software progress, that scheduling power that we've introduced for efficiency.
So this is it's another one of these chicken and the egg sort of scenarios where you have you need the test equipment to test the chip, but you need the chip and the test equipment to test the chip.
It is definitely chicken and egg, and we need a good sniffer. and we need a distributed sniffer. So one advantage Spirent has is synchronized distributed sniffer. We call it synchro sniffer. So for us to really analyze how well the scheduler works, we need to put multiple probes and multiple bands and multiple places in the mesh and analyze it. So yes, we're using a chicken and egg approach with the testing the radios with the radios under test, but we're using them differently. And we have access to the internal microcode to adapt them to do, for example, sniffing, and which you cannot do with an off-the-shelf radio. And we have technology, we've had it for a while, it's patented for synchronizing it, which is really absolute key to testing this kind of a system.
How can engineers test this new management and scheduling to maximize spectrum use?
So we have a reliable way of both doing out-of-band management, doing multi-point to multi-point testing on the IP layer and layer 3. At the same time, monitoring to see how these nodes are behaving. You need to monitor and see if they're switching from 2.4 to 5 to 6 gigahertz bands. We can see what they're doing and how they're making those decisions. We can set up scenarios where it makes sense for all three radios to aggregate their throughput on the backhaul and see if the scheduler does that, if it does what it should be doing, right? If it makes this decision for optimum throughput.
Now, for some time to come, 6 gigahertz band is going to take a while to populate anywhere close to the 5 gigahertz or the 2.4 gigahertz bands. So will the Wi-Fi routers be able to take advantage of that um, while there's more free bandwidth, I'll call it, fewer users in that range, in that frequency band. So do you think is that how it's going to be scheduled, to try to use the 6 gigahertz band, at least for now, until it gets much more populated?
Yeah, no, you're right. It does take a while, but with Wi-Fi being so popular, that changes the game. We're just going to go out there and use that spectrum, because with 320 megahertz channels, even though you have 1200 megahertz available, you're going to gobble it up.
How will Wi-Fi 7 manage the fact that the lower the frequency, the better the range? Is that part of the scheduling function?
So range is a mesh game, right?
Mhm.
It's no longer point-to-point range. It's ability of stations to pick up the mesh node that's near it, right? Instead of sticking on a mesh node that's 2 rooms away, right?
Mhm.
Uh, and the ability of the mesh to serve these clients efficiently and to route efficiently. This is where you need the efficiency on the backhaul. I cannot run my household Wi-Fi on 2.4. I've got 2 high definition TVs that are sitting on one channel. I've got my computer on a different channel so they don't conflict. So I kind of hard configured everything not to interfere, but I know what I'm doing, but most people won't be able to do it. So they rely on the mesh to automate it for them. Regardless of where these stations are, the nearest mesh node will pick them up, and they will be disconnected from the node that's inefficient. For example, 2 rooms away, where they will be transmitting at a low data rate and taking 10 times longer on the air to transmit every packet and keep everybody else off the air. We just can't have that at this day and age, where we have several HD video streams, we have video games, we have other applications that are emerging for the home and the office.
How do you test these various scenarios? You said you need to test on a system level. How do you simulate that, where people are walking into different rooms and the uh, the Wi-Fi has to change bands, it has to change connections? How do you test for how do you do a realistic test for that? A
Well,
functioning test.
yeah. So we have a tool called the tracker. And with the tracker, what you can do is you can take your mesh under test. Let's say it's 3 nodes. You put them in a real house. And then you walk around with devices and you record that motion. And then you can bring that into the test bed and exactly reproduce it. Another thing you can do is, in addition to the motion, you can test an area. For example, you put everybody on the root node, and you want to go and you have, let's say, a dozen stations all doing some high definition video. In that case, you want all the schedule to say, okay, I have all of my resources should go to this front hole because there's nothing hopping on the back hole. I'm on the root node, right? So that's one scenario. Let's see if it does that, or if it keeps some radios on the back hole when it doesn't need to. And then we could go and say we have root, node 2, node 3, and we put everything on node 3. Now it needs to go across the back hole. Let's see how it balances the allocation for the clients on this node 3 that have to go 2 hops out to the internet. We can actually set up all of these test scenarios and one step at a time test the scheduling logic and the roaming logic.
When do you expect Wi-Fi 7 standards to be frozen and adopted?
The Wi-Fi Alliance is already doing a plug fest. That typically means less than a year to market.
Fanny Mlinarsky, thank you for meeting with us. For EE World, I'm Martin Rowe. Thank you for watching.